what were the old plate tectonics? What happened before the modern plate tectonics? We just, we have a snapshot of what's going on the planet today. But the planet's been around for an awful long time, so I'm trying to see, okay, so these rocks in this mountain, or maybe this boring bit of paddock somewhere, just sticking out of the ground, can they tell me something about an ancient mountain range or an ancient collision between different plates?
Hello and welcome to Wonder, brought to you by the Geoco. I'm Holly Cook, as always joined by fellow Earth scientist Dr. Anthony Reid, and today we're sitting across 4 rocks, a tube, some toilet paper, and Professor Alan Collins from University of Adelaide. It is such a treat to have Alan here, especially as we've gone through the magic of continents, early Earth, and honestly, we've just exploded onto the tectonic scene. We're looking at why is it ever changing, and why has he brought these beautiful, sparkling rocks with him? What stories do they reveal?
Pamplona is a great town and a great city in northern Spain, and you can watch the bull runs in there. But there's other things you can see in that town, and one of those things is the Pyrenees Mountains. Now, Alan, you're a bit of an expert in Pyrenees geology, but, from the Pyrenees, let's just walk our way through European kind of continent. And what else can you see?
Well, the Pyrenees, that's where Iberia, Spain and Portugal crashed into France. But as you see, you've got this big high mountain range that then cuts across over towards the Mediterranean and then zips up through Switzerland, Austria, forming the Alps.
So that's the European Alps.
Yeah.
Right.
I was there over the winter.
There you go.
Place.
Lucky you.
There you go. And if you follow it, you can see it just sort of carries on. It goes through Austria, Slovenia, then through the Balkans. Yeah. Comes the Carpathians. There's a big loop that's just north of where you got there, through Romania.
Ah. Oh, yeah.
But it's like a big, it's a big branch that comes off it and comes back again. And then through Bulgaria and into all those mountains of Turkey, very distributed through Turkey. You have all these mountain ranging, see how mountainous it is there.
Yeah, wow.
And then heads, right the way through the Caucasus, Georgia. Azerbaijan, Armenia.
They're still going. We're still in the same system.
It pretty much, yeah. The details are different, but really it's all part of the same collision between different bits that came off Africa or came off Antarctica or even Australia as we get further east.
Keep going. What else do we see?
Moved up and smashed into Asia.
I love looking at I love looking at Iran on Google Earth. I just think, what is happening to the landscape here?
Oh, I know. If you take the plane, if you get a plane to Europe from Australia, you often just clip into the southern bit of Iran there, and it looks amazing out the window.
And now we're in the Himalayas.
Yep, you do that little. Does that sort of right angle turn at Pakistan, and then it does another right angle turn over North Pakistan, southern Tibet, Nepal, India, Bhutan, all those amazing countries, amazing places. Highest mountains in the world, and look how wide Tibet is as well. Tibet has an average elevation of 4 kilometers high. I mean, that's ridiculous. 4 kilometers, there's nothing in Australia that's as high as 4 kilometers anywhere. But that's the average.
That's the average. Yep.
Yeah.
Does it stop here? Is this?
No. Well, look, you can see
keep going.
It keeps on going. It goes and turns around, and then
look, it does.
Heads on down through Myanmar. Heads on down through Vietnam. It's not so obvious. It's a bit more distributed. But that Malaya Peninsula through Malaysia, and even then, you sort of start to lose it as you come into Indonesia. But really, that those mountains are really the same system as the Alpine Himalayan chain. It hasn't turned into this big, 4,000, 5,000, 6,000, 7,000 meter high mountain range. But it will one day, actually. It's actually what we're looking there is a snapshot of what a lot of the Himalaya was like before.
Fast forward, we're in Indonesia. We're coming up through Myanmar, through the Himalayas, through this stunning, complex landscape. Iran, we're up in the Mediterranean, through Greece. We're doing our Euro holiday in the mountains, and we're back in Spain.
Watching the bulls.
So
run.
That was quite an excursion. That was quite a run.
Yeah.
Amazing stuff.
So what business of all of those places, feels like we just went halfway across the earth. What business of all of those got being the same system? What? Why?
Why? Please explain.
Why, Alan?
Well, I guess, if you went to the moon or something, you looked on Earth from a long, long way away and you sort of, you closed your eyes and squinted a bit, you would see a big continent on the north, right? Asia, right? Asia and Europe all join up, and they're really just one big entity. And then you'd see to the south, you'd see these other continents. You'd see Africa, and you'd see, I'm forgetting the Americas, let's ignore them for the moment.
For now.
And you'd see Antarctica, and you'd see Australia. And what's happening is a lot of these continents, Africa's sort of just rotating around. Australia, we're moving rapidly north. Antarctica's sort of still stuck there, doesn't really know where to go. But India has also just come off Antarctica in relatively recent times, like Antarctica and Africa, and it's moved north. And they're all moving north and smashing into this big northern continent. So that, you could summarize an awful lot of the plate tectonic geology of the world, or at least half the planet, if you're just looking at half of the planet, from that really, these continents that are moving north and smashing into this northern continent. It's what's going on in the Pacific, and the Americas, as I say, is a little bit different, but
this is a significant chunk of the world.
Yeah.
Huge chunk of the world.
Yeah.
And you said recently.
Recently. Well, it's going on today. It's still happening.
Yeah. Actually, we talk about the Himalayas still growing.
Yeah. Himalayas are still growing. That's what earthquakes are. That's why we have all these horrendous earthquakes in places like Turkey. The earthquake earlier was it still this year? I can't remember. Or last year, that huge one in Turkey. That's all part of this system. It's all part of these southern continents sort of moving around, working their way up and grinding into these northern continents, I suppose. And as I say, when we get over to the east, when we get over to Indonesia, that's what we're seeing there are the mountains that are forming by the northern motion of Australia. Now, to the north of the continent of Australia, we've got ocean, and that's being subducted, going down into the deep earth. But Australia's following it as the continent. It's going to hit that, and it's going to create more mountains over in Indonesia.
Righto.
Not tomorrow, but it will happen in...
Don't hold your breath.
Yeah, exactly. Geological time, not much geological time.
Right. And what I know about you is you're a man of the field, Alan. You are always in some awesome pocket of the world, but
I know. He's in Mozambique or Madagascar.
I do like Madagascar.
Stop it.
Kenya, I know.
Unbelievable.
Don't say that. This is the real reason I do geology. I don't. The people who pay for it don't have to know that.
Should we edit that out? Is that
no way. It's on the record. So my question is I actually don't think you're there, though, admiring obviously the present landscapes are incredible.
Of course.
But we know that you're not there to actually look at the present landscapes. There's stories in there that are much more ancient.
Course, yeah.
So what are you doing in these beautiful places if you're not admiring today's landscape? What are you trying to access?
Well, at one level, actually, just trying to sort of see through the present, I suppose. See through. I know, I got into geology because I loved mountains and walking around mountains. But I guess what I learned, I think what a lot of us learn is there's so many stories in those rocks. Now, a lot of those rocks are nicely exposed in mountains, so it's brilliant. So we can go and see them, we can try and work out why those mountains are there. But of course, they preserve so much more information about what was there before those mountains were there. And I guess I try to learn how to look at those rocks and try to work out really what happened what were the old plate tectonics? What happened before the modern plate tectonics? We just, we have a snapshot of what's going on the planet today. But the planet's been around for an awful long time. So I'm trying to see, okay, so these rocks in this mountain, or maybe in this boring bit of paddock somewhere just sticking out of the ground, can they tell me something about an ancient mountain range or an ancient collision between different plates? And then you go, well, that's wonderful, but can you sort of stick that together to make an ancient plate jigsaw? And that's when it gets fun, and that's where you have to go to all weird and wonderful places because that's where the evidence is. So you could argue I've turned my whole career into being a way to get to obscure parts of the world that they're fun to visit.
So you're telling us that what we see now is just a snapshot in time, obviously, and there were a whole series of ancient,
absolutely,
mountain belts and ranges and
sedimentary
oceans, and they're all gone. Yeah. And all that's left of them is what's recorded in your fantastic
this is just
I did bring some toys. Absolutely that. The information that's in the rocks that we walk over, that we look at, that we drive past. They're snapshots or capsules of what's happened to the planet in that one place, or even sometimes they come from somewhere else, and we just need to learn how to read it.
I think this is hilarious. I'm going to pick what I think is probably the most boring. I actually think this is the most boring looking rock here. But what I want you to do is prove me wrong. Because like you can't just thump you can't just thump this kind of stuff on the table and expect me to pretend it's not there. I'm going to pick this one.
This one.
Why did you lug that around?
It is
from the university
I
here?
agree. I actually show these to first years, and one of the lectures in the first years, I get people to pass it around. They look at it and go, "It's a dull looking rock. It is a dull looking rock. Look, it's got a few funny little white blobs on it, and it's pretty brown, and it's a bit the colours sort of smear into each other." But this comes from a part of West Australia, huge place. Comes from a place called the Jack Hills, which is in Murchison, which I think has about 13 taxpayers in a place the size of Belgium. They're always the size of Belgium, aren't they? But it is about the size of Belgium. It's something like, I'll get a number of, but it's that always. It's definitely within that order of magnitude. Yes.
Jack Hills. I reckon Jack Mulder brought the Jack Hills up. You're about to talk about zircons.
I know, I've actually got some. No, grains of sand. Some of those grains of sand are zircons. They're the interesting ones. And so this is this has the oldest thing in the planet, or the oldest material that formed on the planet. Now, I'm going to say it definitely has because, of course, I haven't analysed all those grains of sand.
This particular piece.
But there is a huge potential that particular piece may well have the oldest thing that has ever formed on the planet.
I'm willing to accept a creative license.
Exactly. A rock right next, that came from the so-called Discovery Outcrop, where the grains of sand that rock is made of, as well as those pebbles, one of those grains of sand came out at 4.4 billion years old. 4,400 million years old.
So if the grain of sand came out at 4.4 billion years old, does it have a history before that?
It does.
Date?
Yeah. And no one knows where it came from, right? We'd have no rock on the planet older than that.
Yep.
But it's a grain of sand. You're absolutely right. It eroded from something else that existed. So there must have been something older. The planet is older. We do know reasonably well the age of the planet, and the planet is about 250 million years older than that grain of sand. But at that time, that's like a blink of the eye. So there were stuff around. And it's actually it's been in the news this week because some of these grains of sand that get older than 4 billion years, they have chemical information locked up in them. If you can imagine, just a bit of sand has a chemical information locked up in it that people can interpret to mean there was actually fresh water and it rained and the planet wasn't a big magma ocean as we always see it in
cartoons
and popular science things. It wasn't just red and magma everywhere, and it wasn't. It was raining and there was water. It was less than 100 degrees C on the surface.
That makes my brain blow up.
It makes your brain blow up. I have to do this for a job.
Come on, girl, you've got a whole career.
Yeah.
Unreal.
Yeah. So that's. Oh, the rock isn't that old, right? The rock is still old. This is still a couple of about 2.5 billion years old, a bit older than that.
So the sediment itself is formed in about 2.5 billion years ago with some sort of river
system. Yeah, exactly.
So the river flowing through some part of what we now call Western Australia 2.5 billion years ago, eroding away material.
Yep.
And when you analyse the age of that material, you find that some of that material is as old as 4.4 billion years, at least 250 million years.
Yeah.
Only 250 million years younger than the age of the formation of itself.
Yeah. Isn't it? It's amazing, isn't it?
Take the steak knives with this one because it's got evidence for fresh water at that time.
I know. It's ridiculous.
It's incredible what you can find out from these rocks.
It is incredible. And it actually changes. So that time period, that eon before 4 billion, we actually call Hadean, like Hades, like
hell.
Hell. and of course, now what we know from this paper from last week is that it wasn't. It was actually quite nice. It was, raining and
maybe not a lot of oxygen.
Yes, I don't think. You wouldn't be going there on holiday.
I just started doing the budget for the Geoco field trip.
No,
but you wouldn't be burning at least.
No, you wouldn't be standing on magma like somewhere in the middle of Iceland.
Exactly.
So, Alan Collins, if your job is to understand these rocks, and we've just gone and said there's evidence of 4.4 billion years of Earth,
history,
what do you? This is a totally unhinged question. What do you think are some of the biggest changes the Earth has seen in 4.4 billion years?
Oh, well, that's it. That's an easy one.
An
easy one. That's plate tectonics. Again, most people would say,
great
life,
answer.
right? Life,
great answer.
Yeah. Well, life's just a funny little thing. But plate tectonics is the real reason. We don't know of any other planet that has anything like our plate tectonics. And what we mean by plate tectonics is arguable. Everything is. But really what I mean by it is reasonably rigid bits of the Earth, plates, that are moving horizontally or around the circumference of the planet and knocking into each other, ripping away from it, smashing into it, bits going down, bits going up and forming mountains. And we don't know of any other planet that does that. There are some moons of some of the icy giants that have ice that sort of might do that a little bit, but it's just ice, right?
It's a bit.
It's a bit late.
I mean, you're really.
But there's certainly all the terrestrial planets and we have nothing like it, nothing like it at all. Which is weird, right? Why not? Venus is very, very close to us. Mars isn't that far away from us. Venus is about the same size as us. Mars is a lot smaller, but Venus is about the same size of us. Doesn't seem to have had anything like plate tectonics on it. And so there's a growing body of thought that really is suggesting that this incredible phenomena we have is actually responsible for an awful lot of the things that make the planet weird. Oxygen in the atmosphere, life, us running around, destroying our lovely habitable planet. Even the concentrations of the resources we use, the metals we find, all that sort of stuff.
Is a consequence of plate tectonics.
There's again, I'm going to stick my neck out. Yes, definitely.
We love
plate tectonics
at the biggest scale,
at the biggest scale. Yes, plate tectonics seems to be one of the if not the underlying control on most of those phenomena. And it's something we're only, I think, from even just conceptions of people are only really tying together from the last, I would say, 10 years. But even there's papers that come out on this every couple of months on some other little bit that, that seems to fit in with that seems to fit in with this, that goes back to plate tectonics. It's incredible.
What's cool is I'm pretty young. And I know.
Getting older every day.
Wrinkles each day.
Keep going.
As like more mature people, we can
That's
say
right. By implication, the rest of us are not. But anyway.
What's cool is coming into uni, you kind of just sort of, when you learn all this amazing stuff, you sort of just take it at face value and you think, this piece of knowledge always has and always will be. And I reckon I just get really unseated by hearing, I respect you guys a lot, and hearing people go, no, this is new. Like you said, every couple of months, people are still putting together new things. That's just so startling because this is how our Earth works. This is a grand theory of Earth.
When I was a student, and which was a long time before when Anthony was
I think I've called people old on every episode.
Stop that.
Keep going. That's all right.
But I looked back at the time when plate tectonics was discovered, the late 60s and early 70s, which was long before me. And I thought, that must have been amazing, this sort of revolution in science, in earth science. And I thought, everything's sort of, it's all pretty done now. We know it. We're doing cool stuff, but it's all just sort of filling in the things. But do you know what? I think the last 5-10 years, we're actually going through a similar revolution. We don't necessarily, I think people in the late 60s and early 70s didn't actually realize they were in a scientific revolution. We're in a scientific revolution now. And it's coming from, technological advances, but it's also coming from the integration between a lot of different science that's being applied to the Earth. I mean, that's all geology is. It's just science applied to the Earth. And really understanding just how interlinked, interconnected it all is. And yes, we've got better technologies that are step changing. We can date so many more things, which gives us that sort of, it allows us to put the library in order, if you like. What happened when. We've got so much time to play with. We have to sort it out to know, when did that phenomena happen, and when did that phenomena happen, and where was this thing at that time? So we're getting that in place. But also, again, as I say, there's so many people applying maths or biology or biochemistry or physics to really try and see how these things interact. It's staggering. It's impossible to keep up with, but it's amazing when you see what can be produced.
And I reckon there's, to call to your library analogy, there's a certain part of Earth's library which you hold in your heart dearly. There's a certain billion years. And I reckon we gave Indrani the chance to say why it wasn't the boring billion.
The brilliant billion.
The brilliant billion.
It
was awesome. So what's up with the brilliant billion?
Yeah, the brilliant billion. Earth's middle age is another term I think is quite reasonable. I also agree with her that boring billion is anything but boring. So that's this eon we call the Proterozoic, and it's always been the bit in between, right? The Phanerozoic, the time of abundant life, is where all the fossils are. That's the last little bit on the top, the last 500 million years. And the first bit, of course, that's the formation of the planet, the big stuff.
Magma oceans.
Magma oceans.
Which we thought existed, but may not.
All of that sort of stuff. It's cool and wacky, and that's obviously really weird. But then there's this it's actually not 1 billion, it's 2 billion years of history, which is the Proterozoic, which is the bit in the middle. And that's the bit where this alien world of magma or non-magma oceans,
freshwater apparently,
and you'll have heard people talking about weird lavas that crystallize in funny sort of zigzaggy patterns called komatiites. All sorts of weird stuff happens back there, and it was a strange world back there. But then in the Phanerozoic, the world wasn't, you'd have recognized the Phanerozoic the 500 million years ago. Okay, things
we might
different.
have been able to walk to Antarctica.
We might have been, yes, exactly. It'd have been
but
different, blue oceans. Wouldn't have been much on land, just a bit of fungi or something. But, you've got life on land. You'd have had some oxygen. You might have even been able to breathe at least a little bit. And the climate would have been similar. So, recognizable planet. So wacko, weirdo planet to recognizable planet. 2 billion years. That all happens, and life just happens to, get complicated and interesting during that time as well. And again, I think a lot of it was sort of ignored because it was very hard to subdivide because we couldn't actually date a lot of stuff. Right? That was one thing, and also there weren't really wacky looking things in it. In the Archean, there's lots of wacky looking things. So of course, you go, wow, that's interesting. What does that mean? And so there's lots of rock that sort of looked similar to a lot of the rock we see in the modern Earth, but we didn't really have the tools.
Can you give us
to
some
get
examples of where people might be able to see these kind of brilliant, I nearly said
Brilliant,
boring,
brilliant.
but I know Andrew
bang.
Yeah, that red line through your name still. Good one. Where can we go?
I mean, people use these actually. In Australia, they're quite common. These rocks, they're everywhere.
What rocks are you
right?
talking about?
Yeah, what do
am
they
I
look
missing?
like? What are we?
So forget those nasty eastern states. So forget Victoria and most of New South Wales. But Broken Hill's is full of these. All of South Australia, west of the Murray, west of the Adelaide Hills, really. All of West Australia, all of the Northern Territory, virtually all of Queensland.
Whereabouts in the US? Or in
Whereabouts
Canada?
The US?
Whereabouts can you see these rocks?
A lot of them are caught up the bits are caught up in the Rockies, but also the real flatlands of Canada when you go up into sort of the tundra up in the northwest territories, all of that sort of area, Saskatchewan, Manitoba, Quebec,
Africa.
Oh, absolutely. A lot of Africa. Again, they had these kernels of these old bits, these really old Archean bits. But they're also laced together with the roots of ancient mountain ranges, which are now reasonably flat lands, and they are the rocks that formed and then got deformed as these plates hit each other during these 2 billion years of the Proterozoic.
How much of the continents is made up of these rocks?
Good question. I'm not going to make up an answer.
Between
I reckon
not at the depth. I'm just talking about its surface.
Of say the Americas, of all the continents, I'm going to make a guess of something around about 40%.
Okay, 40% of all the rocks you see at surface.
That's a total guess, but it won't be a million miles off.
Alan Collins 2024.
First com.
Thank you, yeah.
But the point is, there's a lot of material sticking out of the ground, and geologists were fixated on the relatively tiny amount of really, really old stuff. Yep. Or they were fixated on current day, or when I say current day, I mean the last few hundred million years.
Smear on the top. Yeah.
And one of the reasons that they were difficult to get into as a geologist is, as you say, they were difficult to date.
Yeah.
They were difficult to kind of pull apart. And why is that? You've got a piece of a rock sitting here now, a few different examples.
I do. Which one do you want? So, here's a beautiful, pretty one. Right? A big sparkly one. What have I done with this? Oh, that's the other one there. The big sparkly one. So this is it's a lovely rock. This is a rock that was caught up in what we're pretty sure was the biggest mountain range we've actually got any evidence for, which is a mountain range that you can now find the skeleton of it, if you like.
Yes,
in Antarctica.
Skeleton. That is a great way to put it. Yep.
In bits of Antarctica, eastern Antarctica.
Yeah.
The bits, some of the Australian bits of Antarctica, I suppose. but through Sri Lanka, through southern India, through Madagascar, all these wonderful countries you were saying before, Mozambique, Zambia, up through Kenya, Tanzania, Ethiopia, Sudan, Egypt, Arabia.
Huge.
And you can see, if you go to those places, you walk around the mountains, the rocks you're walking on are rocks that have found themselves way, way down, 20 kilometers down in the crust when two huge continents smashed into each other. So it's just like the Himalaya today. And the scale of the mountain range is like the Himalaya today, probably bigger. Again, the only mountain range that competes with this origin, which is known as, the origin is just not a term for a mountain range. The only one that competes is the Himalaya.
Yeah.
So the modern Himalaya, and then this one, which is known as the East African origin. Because there's very good examples in East Africa of it. But it's not just East Africa, as I say. And that formed just about the time at the end of this Proterozoic, these 2 billion years of Earth history, just when things got really exciting, when the brilliant billion turned into the boring Phanerozoic. Just at the end of what horrible people call the boring billion. But just as everything got really wacky, actually, so right at the end of the Proterozoic, the climate did stupid things: super hot, super cold. Before that, it was actually quite stable, we think. Again, there's still lots of work going on it. We think it was quite warm and quite stable for a long time, like billions of years before. But then it went really wacky. And also, life got really strange. Life was around. There's masses of it. In fact, you can argue there was probably a similar amount of biomass back a billion years ago as today. It was just very simple. It was bacteria and archaea and some of these complicated cells, these eukaryotes, algae, but not much. And we sort of can tell they're not much from the chemical traces they leave behind. And then about the time that mountain range started to get going, they started to get really complicated. In fact, they seem to, the earlier bacteria and archaea, we can see quite amazing hints and sniffs in the geological record for them going extinct. The whole series of extinctions, and then these complicated cells take over. These eukaryote cells take over, and then they combine together, and we get metazoans, and we get animals right at the end of this billion years.
So.
Yeah, where are we going to go?
I'm just so impressed. I just love geology. I love this science. I just find it so fascinating.
Yeah.
I'm not often silent.
It's just an amazing story, and we should be silent and should be in wonder. That's the whole point of this conversation, is to go, wow, that's incredible. What I hear you saying is a huge mountain range, not actually dissimilar to the current day
similar scale,
Alpine Himalayan.
Similar length and elevation and width as well.
It was around at a really critical time, and perhaps has some relationship to the evolution and changes in the entire trajectory of life on this planet.
Yeah.
Thanks for joining us.
Very much so. My pleasure. But you should be saying why. How does anyone know that?
I think we're going to be saying why.
It's a lovely story.
Next time you come back.
False. I want you to. I actually need it now. But it's the 60. We're going to meet in the middle.
Okay.
Why? You said that very confidently.
I did, didn't I?
Time to ask, where's that confidence come from?
Yeah, and look, and all of that I'm not confident on, right?
Because you're a scientist.
Exactly. So every bit of that is controversial, and every bit of that is based on hypotheses from hundreds of really, really clever people that have managed to stick, or they've come up with suggestions. That's what hypothesis, just a suggestion. And to be skeptical would be to say, well, that's not scientific. That's just a hypothesis. You've got to test. Hypotheses are useless unless you can test them. How can you test these sort of ideas billions of years ago? And I agree with that. You can't at the moment. So at the moment, I would say that a lot of these wonderful stories we're glimpsing at, or we're coming up with, they're actually not, arguably, controversially, they're not scientific in that they're not testable. So there's a huge push to make them scientific. And so what we need to do that is to make a way you can test these ideas. And so to test an idea, you need to be able to make a model that you can then test. You can run it, right? And you can see whether those parameters you put in work. And
that
to
makes sense at all.
But that model, right? That model is just the planet, right? So the model we want is, what does the planet look like a billion years ago?
Mm-hmm.
Where are the mountains? Where are the subduction zones? Where are the oceans? Where are the rift valleys? Once we've got that, then you've got your model, you can spin it, you can say there's so much chemistry, different elements in the atmosphere. They're going to do their things, oceans are going to circulate, and you can start to see if it rains a lot on these mountains, and if those mountains then erode and they move elements, nutrients into the oceans, and then life takes them up. What does that do to the temperature? The planet's temperature primarily is controlled by weathering of rocks, weirdly, as well as, of course, the sun. Primarily, yeah. But weathering of rocks is actually what really governs how much carbon dioxide gets sucked out of the atmosphere over long time scales. Not things what we're doing, not the scale of what we're doing to the atmosphere, but long periods of time. When we have cold periods, it's because we have mountains that those rocks are reacting with the carbon dioxide in the atmosphere, dragging it out of the atmosphere, lowering the greenhouse gases, cooling the planet. So that's all stuff that can be modeled. That's what happened. That's what people are doing now about, what's going to happen to the climate in the future. We can do that in the past if we have a model of the Earth. And that's what we're trying to get towards.
Unreal. So we went from 4.4 billion years to the next decade of Alan's research. Fantastic.
Right.
Alan, unreal. This
Thank
is
you.
just not the last time. This is just not our last conversation. So it's not a true thank you, but thank you for an awesome
pleasure.
30
That was
minutes.
fun.
And we didn't even get to the last. We didn't even get to the
Next time.
next time.
Thanks,
Cheers,
Alan.
Alan.
Thanks.
Pleasure. Thank you.